So good morning everyone, and we are in chapter 4 today. We finished chapter 1 in the previous lecture, and today we are going to start with chapter 4. Chapter 2 and chapter 3 are introduction to MATLAB, which I have put for you in the blackboard. You can look at the chapters by yourself, see what MATLAB is all about, how to use it. It's just basic introduction to MATLAB. Even what's there in chapter 2 and 3, we are not going to use all of it. We use something very basic and simple. Today we look at chapter 4. Chapter 4 is about round off and truncation errors. So this chapter gives us an idea about what we mean by errors. As we said earlier, that numerical methods are approximate methods. The solution that we get from numerical methods are approximate solutions, and since they are approximate, they end up with some error. So we see what we mean by errors in this chapter. The objectives of the chapter is to understand the distinction between accuracy and precision, learn how to quantify error, learn how error estimates can be used when we have an iterative calculation, see what we mean by round of errors and how computers end up with round of errors, and how computers define numbers, what we mean by truncation errors, and how Taylor series can be used to estimate the errors, and then see some differences in values that we get using approximations like the finite different approximation for derivatives. The first thing that we have is accuracy and precision, something that we have taken earlier in Cheng 111 as well and Picach 111. Just a revision of it. Accuracy refers to how close a computed, calculated, or measured value is to the true value. So how close something is to the true value, that is a measure of the accuracy. While precision refers to how closely individual values or measured values are to each other. So a good way of looking at accuracy and precision is using the bullseye, considering the center of the bullseye to be the true value. We can see in figure A, the numbers or the values are far away from the true value. Hence, we say that they have no accuracy. And they are far away from each other, so we say they do not have precision. So A is inaccurate and imprecise. So there is no accuracy and there is no precision. In figure B, we can see that the numbers are far from each other, so we say that they are imprecise, they don't have precision. But if we take some sort of an average, they might go to the true value, so we can say that it has some sort of accuracy. In figure C, just let me do this and come back. In figure C, we have values which are close to each other, so we say that they are precise values, but since they are far from the true value, we say they are inaccurate. And of course, this is what we desire to have always, to have accuracy and precision. The numbers are close to each other and they are close to the true value. So this is the meaning of accuracy and precision. Accuracy, how close the measured or computed values are to the true value, and precision, how close those values are to each other. We have some definitions for error that we can use when we deal with the approximate values. The first one is the true error. The true error is just the difference between the true value and the approximation. So if your true value, let's say, is 10 and you got a value of 8, then your true error is 10 minus 8, which is 2. So that's your true error. Absolute error is just the absolute difference between the true value and the approximation, because if 10 is your true value, then if you get 8 or you get 12, in both cases the difference between them is 2, but one will give you plus 2, the other will give you minus 2. So the absolute error is just the absolute value, so that we don't deal with plus or minus. It doesn't matter if it is too bigger or it is too smaller, the error is 2. So that's the absolute error. Then we have what we call the true fractional relative error. That is the true error divided by the true value. And we have the relative error, which is given by epsilon t, is the true fractional relative error expressed as a percentage. So whatever you get here, you just multiply it by 100. So if the true error is 2 and the true value is 10, then the true fractional relative error is going to be 2 over 10, which is 0.2. And expressed as a percentage, so the relative error is going to be 20%, which is just this number multiplied by 100%. So that's the definition. ET, the true value minus the approximate value. It is absolute when you have an absolute sign on it. Now, one shortcoming or one problem that we have with such a definition of error, which is the true error, is that it takes no account of the order of magnitude under the value under examination. So order of magnitude means the power of 10. 10 to the power 0, 10 to the power 1, or 10 to the power 2, or 10 to the power 3. So it doesn't take into account whether the number is 1, 2, 3, or whether it's 10, 20, 30, or whether it's 100, 200, or whether it is in thousands. We understand this by this example. Suppose that you are asked to measure the volume of a storage drum and a beaker. And when you measure the volumes, you find out that the storage drum has a volume of 49,995 ml. And when you measure the beaker, you find that it has a volume of 245 ml. Now, if the true values are 50,000 and 250 ml, and you are asked to find the true error, then the true error is the true value minus the approximate value. So for the drum, it's going to be 50,000 minus 49,995, which is 5 ml. And here it's going to be 250 minus 245, which is also 5 ml. So in both cases, we see that the true error is 5 ml. Now, of course, we can realize that having a true error of 5 ml in 50,000 ml is not same as having a true error of 5 ml in 250 ml. Both of these are not same errors when we want to compare them. A better way of looking at the error is using the relative error, whether you use it as a fraction or whether you use it as a percentage. Now, if you compare the values that we have here, for the storage drum, the relative error is given as the true error divided by the true value. So it's going to be 5 ml, which is the error that we found, divided by the true value, sorry, which is 50,000, and it comes out to be 0.01%. However, for the beaker, 5 ml divided by 250 ml comes out to be 2%. Now we can very clearly see that 2% is much bigger than 0.01%. That's almost 200 times bigger. So although the true error is the same, but we can see the relative error is much bigger. This is, for example, if you are asked to find the height of an absorption tower, or you are asked to find the height of liquid in a measuring cylinder. Let's say here it's 7 centimeters. Let's say we have 10 meters. Now if the error in the measurements comes out to be, let's say, 1 centimeter in both of them, then you can see that 1 centimeter error out of 10 meters is not a big error, but 1 centimeter error out of 7 centimeters is going to be a big error. Therefore, comparing true errors does not give us a very good idea about the size of error that we have, but the relative error tells us gives us a much better idea about the errors that we are dealing with. Now, in both these cases, whether you look for true error or whether you look for the relative error, both of them are found by comparing them to the true value. The true value. Now, you have a problem with finding the error if you don't know the true value. Whether you are using numerical method or you are using some other analytical techniques, usually we don't know the true value. We are trying to find the true value. So in this case, what can we do? In this case, then we use some approximations to the error. One such approximation is the approximate percent relative error, in which we use approximate values to find the errors. For iterative processes are trial and error processes, where you take a guess value, you try to find the true value, then you go on to the next trial. These are called the iterative processes, where you keep repeating your trial and error procedures. So in this iterative processes, the error can be approximated as the difference in values between successive iterations. You found some value in iteration 1, you found another value in iteration 2. The difference between these two values can be used as an approximate to the error. The approximate percent relative error is given as the approximate error divided by the approximate value multiplied by 100%. For iterative procedures, we can write this as the present value minus the previous value divided by the present value of the current iteration. It says here the relative errors, the true or the approximate, can be positive or negative depending on whether the value here comes out to be true or positive or negative, but usually we represent them as absolute values. So to only get positive values, we don't use negative values for errors. When dealing with errors, we try to repeat our calculations until we reach a certain pre-specified tolerance. Tolerance means the error that you can accept. We define that as epsilon s, where s means the stopping criteria. So in such cases, the computation or calculation or the iterative process to find the approximate values is repeated until the approximate error remains less than the stopping criteria. So we call this the stopping criteria, epsilon s. We can also relate the stopping criteria to the number of significant figures in the approximation. It is how many significant figures you want to have in your answer, how many the precision that you want in the answer. And it can be shown, according to this paper written by Scarborough in 1966, that if the following criterion is met, then we can be assured that the result is correct up to n significant figures, which is if you use the stopping criteria of 0.5 multiplied by 10 to the power 2 minus n, where n is the number of significant figures that you want in your answer. So for example, if you want 4 significant figures, then you use 0.5 into 10 to the power 2 minus 4, which is 0.5 into 10 to the power minus 2, which is 0.005% as your stopping criteria. If you are going to stop your calculations at an error of 0.005%, then you can be guaranteed that at least your answer is going to be correct up to n, which is 4 significant figures. Of course, it could be accurate to more than that, but at least we know that it's guaranteed that we will have at least this much accuracy in the values. We look at this example. I'll copy it with me to whiteboard. It says in mathematics, functions can often be represented by infinite series. For example, the exponential function is given by this infinite series. Exponent of x is 1 plus x square over 2 plus x cube over 3 factorial plus x4 over 4 factorial plus x5 over 5 factorial, and so on. The more terms we add, the approximation becomes better and better to estimate the true value of the exponent of x. He's saying starting with the simplest version, exponent x equal to 1, which is just taking the first term of the series. He says add terms one at a time in order to estimate exponents of 0.5. So x is 0.5. After each new term is added, compute the true and the approximate percent relative errors. Note that the true value is 1.648721. Add terms until the absolute value of the approximate error estimate falls below a pre-specified error criterion epsilon s conforming to 3 significant figures. Now, epsilon s, we said, can be given by the equation 0.5 into 10 to the power 2 minus n%. Now here he's saying up to 3 significant figures, so n is equal to 3. So this is 0.5 into 10 to the power 2 minus 3, which is 0.5 into 10 to the power minus 1, 0.05%. So that's our stopping criteria. Now, the simplest version, he's saying when we add only one term, this is number of terms, exponent of 0.5 is 1. And then we can find our true error as the true value, which is 1.648721, minus 1 over the true value, absolute value, which is multiplied by 100%. So let me find this value. One 1.64872 minus 1.
39.34.
That comes out to be 39.35%. And we can find the approximate error as the current value minus the previous value divided by the current value Now the current value is 1. What's the previous value? The value that we had in one iteration before this. Of course, this is the first iteration, so we don't have an iteration before this. Since you don't have an iteration before this, then please don't find an approximate error. This is very important. Please keep it as a note in your mind always. Approximate error cannot be found in the first iteration. Why cannot it be found? Because there is no previous value to compare the current value with. Okay, so we cannot find this value. Now we go to the second iteration. Exponent of x, or I'll say 0.5 because we are dealing with 0.5, is approximately equal to 1 plus, according to the equation, 1 plus x squared by 2. So we need to add one more term, which is 1 plus x. And x, of course, we know is 0.5, so it is 1.5. And we can find our true error as the true value minus the approximate value divided by the true value multiplied by 100%.
%9.02%.
So 1.64871 minus 1.5. So it comes out to be 9.02%. So I'm just going to write it 9%. Now we found the value for the true error, and we can also now find the value for the approximate error because we have a previous value. The current value is 1.5. The previous value was 1 divided by the current value because we expect that whatever we found now is better than what we had in the previous iteration. So that's 1.5 minus 1 is 0.5 by 1.5, so that's going to be 33.3%. The stopping criteria that we are going to use here, which we said is the 0.05%, we are going to compare it with the approximate error, not with the true error. We'll use the approximate error, not the true error, for the stopping criteria. Now for the next term, we add one more term. So 1 plus x square over 2. One plus x square over 2. .625, and we can find our true error as 1.44%. You can see that the error is reducing. If that in the test you come and find out that the error is increasing, then of course it shows that you don't understand the basic concept that the error should have been decreasing and not increasing as you add more terms. So this is going to be the current value minus the previous value divided by the current value. And that comes out to be 7.69%. Of course, 7.69 is still much bigger than 0.05% error, so we have to continue with more iteration. So 1 plus 0.5 plus 0.5 square over 2 plus 0.5 cubed over 3 factorial. One point it's divided by 3 factorial. So x cube divided by 3 factorial. So I find it to be 1.645833, and you can find your true error as 1.648721 minus this value, and it comes out to be 0.175%, and you can find your approximate error as the difference between the current value and the previous value, which is 1.645833 minus 1.625. So it comes out to be 1.27%. Of course, we see that even the approximate error reduces with each iteration. Then adding another term, approximate value of 0. Exponent of 0.5 is 1 plus 0.5 plus 0.5 square over 2 plus 0.5 cube over 3 factorial plus 0.54 over 4 factorial. It's 1.64. Right? And of course, we can find the true error comes out to be 0.17%, and we can find the approximate error comes out to be 0. So it's starting to come down. Maybe it will go less than 0.05% in the next iteration because we reached 0.15. So let's try another one. So that's 1 plus 0.5 plus 0.5 square over 2 plus 0.5 cube over 3 factorial plus 0.5 to the power 4 over 4 factorial plus 0.5 to the 5 over 5 factorial. So it's 1.648698. And the true value or the true error comes out to be 0.0014%. Of course, the true error has gone much below than the stopping criteria, but we don't use that. We use the approximate error. And we find the approximate error comes out to be 0.016% error. Of course, we have to go below 0.05. All these things get merged together. So we were supposed to be less than 0.05, and what we have now is 0.016. So 0.016 is, which is less than 0.05%. So we can stop here. So we see how adding the terms makes the error come down, and we have seen how to find the true error and how to find the approximate errors in the different values that we obtain. This is what we have here. We have seen the different values that we found, and the true error and the approximate error in each of the values that were found. I'll go to the book and we try to solve a problem related to the same material. Chapter 4, problems. I'll look at problem 411. Just copy the problem there first. Okay, it says the Maclaurin series expansion for cosine x is 1 minus x squared over 2 plus x4 over 4 factorial and so on. Starting with the simplest version of cosine x equal to 1, add terms one at a time to estimate cosine of pi by 3. So x is pi by 3. After each new term is added, compute the true error and the approximate percent relative error. Use calculator or MATLAB to find the true value. So we can first find the true value. Of cosine pi by 3. Please, when you are working with your calculators, make sure you work with radians when dealing with numbers. So the answer that I get for cosine pi by 3 is 0.5. So that's the true value. Now we start adding terms one at a time. So the first one, cosine of pi by 3 is approximately equal to 1, and the true error is the true value minus the approximate value divided by the true value. Take the approximate multiplied by 100%. So that's 0.5 minus 1 is minus 0.5. Minus 0.5 or 0.5 is 1. So minus 1 into 100, absolute is 100. So 100%. Of course, keep in mind always that since this is the first iteration, so EA cannot be found in because we don't have a previous value to compare our value with. Then we add another term. So we are saying cosine pi by 3 is approximately equal to 1 minus x squared over 2. So 1 minus x squared over 2 So 0.4517, and we can find the true value of the true error as 0.5 minus 0.4517 over 0.5 multiplied by 100%. Okay. Now since we have the previous value, so we can find the approximate error as the current value minus the previous value divided by the current value. One to 1.4, so 121% error. Of course, when do we need to stop? If we read the question, it says stopping criteria conforming to two significant figures. So using this, we can find our stopping criteria as 0.5 into 10 to the power 2 minus n, which is 2%. So that is 0.5%. So we have to stop when the approximate error goes below 0.5%. Of course, currently it is 121%. So we have a long way to go. So cosine pi by 3. Now adding one more term. 1 minus pi by 3 square over 2. And please see now it's minus and then it becomes plus. So plus pi by 3 to the power 4 over 4 factorial, not over 4, but over 4 factorial. Zero point 5018, and you can find the true error as 0.5 minus 0.5018 divided by 0.5 0.36%, and we can find the approximate error as 0.5018 minus 0.4517. Is it, or I'm mistaken? No, it's my mistake. I haven't changed the value. So it's 9.98. You're right. Okay, so still it's not less than 0.5%, so we continue. So cosine pi by 3 is approximately equal to 1 minus so plus, then it will go to minus. Yeah, so let us not round it off. So it's 0.4, then we have 3 nines, and it is 6, 5. So that's the value. We can find the true error. Of course, that's going to be the difference between this and the true value. So it's 0.007%. And we can find the approximate error comes out to be 0.37%. Of course, 0.37% now has become less than the stopping criteria, which is 0.5%. So we stop here, and that's the value that we have to find. So this is finding the true relative errors and the approximate relative errors in an iterative procedure. Important thing to remember that in the first iteration you cannot find the approximate error because we don't have a previous value to compare with. Another thing to remember that we can relate the stopping criteria to the significant figures, and we can use this equation to find the stopping criteria. When you use the stopping criteria, you compare it with the approximate error, not with the true error. You compare it with the approximate error, not with the true error. So even if the true error here was less than 0.5%, you don't stop here because you are comparing it with the approximate error, not with the true error. Okay, so this is the problem which is similar to the one that we took in the example. Any questions? Okay, let's take a 5 minutes break and we come back. Okay, welcome back. Let us continue with our lecture. So we go to the next topic, which is about round-off errors. Numerical methods have been present from a long time, but people were not using the numerical methods because they take a lot of time and calculations, and a lot of effort has to be put into it. And at the end, as we have seen, that we get some approximate values, we don't get exact solutions. However, once computers came into picture, then numerical methods became popular. This is because computers can do the calculations much quicker, and they can do them with more accuracy, and they don't make mistakes, and they don't get tired, they don't get bored while repeating the same calculations. As humans, if we are going to repeat the calculations, as seen in the example that we have taken, that if we are doing the calculations and then we might make mistakes in finding the values, or we might get bored or tired after some time, and then we start making mistakes in the calculations. So once computers became popular, then numerical methods also became popular, and people started going to numerical methods more. Once we use computers for numerical methods, then we end up with round of errors. And round of errors come into picture because digital computers cannot represent some quantities exactly. Quantities means numbers. So the way that computers work, they are not able to represent the numbers exactly. And this is very important for engineering calculations because if numbers are not exact, then we can end up with results which have very big errors. And in certain cases, they can lead to the calculation becoming unstable, where you start getting very big numbers, or you start getting numbers which don't make any sense. There are two major aspects of the round of errors that are involved in numerical calculations. The first one, that digital computers have size and precision limits on how they represent numbers. And the second one is that some of these numerical operations that we do, the calculations that we are doing, some of those operations, they are very sensitive to round of errors. Even if you have small errors, then the results that you get because of doing this operation, the mathematical operation on these numbers, you will end up with a very big error in the results. Let us first see how a computer represents numbers. So the fundamental unit where information is stored in a computer is called a word. And a word is made up of bits. Bits is a short form of binary digits. So they took the B from here and the ITS from here, and they made it bits. So these are binary digits. Binary digits because digital computers, they work in the binary system. So the numbers that they have, there are ones and zeros. So you have a word consists of bits, and these bits have binary digits into them, and this is how a number is stored in a word. The method that is used to store numbers in the computer is called the signed magnitude method, because a number could be positive or negative. Therefore, we have to have a sign, and of course the number has some value, has some magnitude, so it's called the sign magnitude method. The first bit of a word, we said we have a word consists of many bits. The first one is saved for the sign, where a 0 indicates a positive number and 1 a negative, because bits means either you have zeros or 1, nothing else. So if you have 0, then it's a positive number. If you have 1, then it's a negative number. And the remaining of these bits are used for the actual number. Now, how the number is stored, of course, is in binary form. It's not stored in the decimal form. So you can see, for example, 0 in base 10, when it goes to base 2 is 0. This is 1, 1, 2 becomes 10, 3 becomes 11, 4 becomes 100. So you can see just by reaching 4, you have reached 3 digits already. By the time you reach 8, you go into 4 digits. You can see a number like 173 given here as an example takes 1, 2, 3, 4, 5, 6, 7, 8. So it uses up 8 digits to define this number in the binary form. Now, if you use such a scheme to store numbers, then of course you are going to be definitely having a limited range of numbers that you can actually store in the computer. Assuming that you have a 16-bit word size, and then if you use one of the bits for the sign, then you will be left over with 15 bits in which you can actually save the number. So these numbers are going from 0 up to 11111. If you put 15 ones, that's the biggest number that you can get. Then if you convert this into the decimal form, it comes out to be 32,767. So that's the maximum number that you can store in a 16-bit word size, 32,767. The smallest, of course, then goes to the minus sign. So if you have a 0 here, it's going to be positive. If you have 1, then it's going to be negative. And then you can put all ones there to get 32,767. So you can go from minus 32,767 up to plus 32,767. Of course, you can have 0 followed by all zeros, and that will mean plus 0. You can have 1 followed by all zeros, that will mean minus 0. Now, plus 0, minus 0 makes no difference. A 0 is a 0, whether it's plus or minus. So instead of defining minus 0, we can take that definition to add one extra number on the negative side, so that the range becomes from minus 32,768 up to plus 32,767. So that we define one extra number. For an n-bit word, then the range will be from minus 2 to the power n minus 1 up to 2 to the power n minus 1 minus 1. Minus 1 on the positive side, because as we have seen that we use the minus 0 as an extra in the negative side. 32-bit will go from minus 2,147,483,648 up to 2 billion. So from minus 2 billion up to plus 2 billion something you can define in a 32-bit word size. So you can see the limitations that you are getting for defining the numbers. Now, this is if you are only dealing with integers. Integers means whole numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But we know that we don't only deal with integers. We have 1.1. We could have 2.356. So we have also decimal places. How to deal with decimal places. Now, to understand that, let's just look at this example 4.2. Suppose you have a hypothetical. Hypothetical means imaginary, not something real. Base 10 computer. Computers are not base 10. Computers work in binary form. They're base 2. But just to understand the numbers, because working in base 2 is a bit more complicated. So let us have an imaginary base 10 computer, which has a 5-digit word size. So the word size is 5 digits. So it has 5 digits. 1 digit is used for the sign. So that goes for the sign. And the remainder 4 are going to be used for the number itself. Now, from these remaining 4, 2 are used for the exponent. And the 2 remaining ones are used for the mantissa. that is the mantissa, that's the exponent. Okay, that's what we mean by mantissa and exponents. So we have one bit used for the sign, we have two for the mantissa, we have two for the exponent. Of those two that we have in the exponent, because exponent could be plus or minus, one again is used for the sign of the exponent, and we have one digit remaining for the exponent number. So that's how we divide the bits into its different components. He's saying a general representation then can be given as S1 for the sign, D1, D2, because we have two digits for the mantissa, multiplied by 10 to the power. S0 means the sign of the exponent, and D is the digit that you can have for the exponent. Now, using this definition, the largest number that you can have, if you use this for the sign, then taking that to be plus, the maximum number that you can have is 9.9 multiplied by 10. Again, if we make the exponent to be positive, and the maximum number that we have is 9. So that's the biggest value that we can get. Of course, on the negative side, you can have minus 9.9 in 10 power 9. That's going to be the largest negative value, or the smallest negative value, however you want to look at it, that you can have on the negative side. The smallest positive value that we can have is 1.0. Of course, you cannot say 0.1 because that doesn't work. You must have some number here before this. So into 10 power, of course, if you make it minus 9, then you are going to have the smallest value, because 10 to the power minus 9 is smaller than 10 to the power minus 8. So having the 9 here makes the number smaller because we have a negative sign there. So that's the range that we can get. The maximum number is going to be 9.9 in 10 power 9. So from minus 9.9, 10 power 9, up to plus 9.9 in 10 power 9. Also, the smallest positive value that we can define is 1 into 10 power minus 9. What does this mean? It means that any large positive value greater than 9.9 into 10 power 9 goes into what we call an overflow error. I'll go to the next slide, which gives us a diagram to look at it. So that's the maximum positive value, 9.9 into 10 power 9. Anything greater than this goes into an overflow. Sometimes if you have calculators, you find those old digital calculators, they used to give you something like an error like this. This is when you try to define a very big number, it goes outside the range of the calculator, then it gives you an error sign like this. Shows you that you have reached an overflow. Some calculators directly give you the error. If they have this text screen, then it just directly writes for you overflow error. It means that you have defined a number which is too big for the computer to represent. Or same thing on the negative side. So anything bigger than this on the positive or negative goes into the overflow error. In a similar sense, for very small quantities, which is smaller than this, so if you have 1 into 10 power minus 10, for example, that goes into, we call it a hole at 0. This is an underflow error. So anything between minus 1 into 10 power minus 9 and plus 10 into 10 power minus 9, all of this goes into a hole. When we say hole, it means that all of this is converted to a 0. So anything less than this directly goes to a 0. So it cannot define it, it will just convert it into a 0. Similarly, between the numbers, let's say between 0.99 and 1, we have a hole. Which is of the size of 0.01. Similarly, here we have size 0.01, that's a hole size. What do we mean by this hole size? It means that we can define 0.98, we can define 0.99, but you are not going to be able to define 0.983 because you don't have any space for that. Why don't we have a space for it? Because we have only 2 digits here. So you could define 9.8 into 10 power minus 1, which will be 0.98, or 9.9 into 10 power minus 1. But you cannot define 9.83 into 10 power minus 1 because you don't have another digit to do that. So this is truncated, it's cut off. So your number will automatically become 9.8. So anything that falls in between, it's a hole here, it goes to the bottom value. So it becomes 0.99. So even if you had 0.997, it's going to go down to 0.99. So it's not going to be defined as 0.997. Once you go to bigger numbers, then the hole size becomes even bigger. You can see between 1 and 1.1, you define 1.0 into 10 power 0 and 1.1 into 10 power 0. So you get 1 and 1.1. The whole size between them is 0.1. Here it was 0.01. Here the whole size becomes 0.1. So you could define 0.98, but you cannot define 1.02. You cannot define 1.08, for example, because you have 1 and then you have 1.1. So 1.0, 1.1. You cannot have these extra significant figures here. As you go bigger, the whole size becomes even bigger. So, for example, the go ahead. Why it is bigger? Because you can see from here, you have 1.0 and into 10 power 0 and 1.1 into 10 power 0. So this means 1.0, this means 1.1. Why it is bigger? Because the difference here is same. You have 0.1. Before it was 10 power minus 1. Now it is 10 to power 0. If it becomes even bigger, 10 to power 5, for example, then 0.1 into 10 to power 5 is going to be very big. The extreme case that you are going to have is the largest possible number is 9.9 into 10 to the power 9. What's the next number below this? Is going to be 9.8 into 10 to the power 9. And what's the whole size here now? It's 9.9 into 10 to the power 9. If you subtract them, you'll get 0.1 into 10 to the power 9. That's a whole size of 100 million. What do you mean by a whole size of 100 million? It means, for example, that let's say the bank in which you are putting your money works on this system and is having this computer for storing the values. Then if you go and deposit 9.86 into 10 power 9, which is 9.86 billion, the computer cannot store it. What it will store it as 9.8 into 10 power 9. So you are going to lose this 0.06 into 10 power 9, which is 60 million. So 60 million
dinars, let's say, is lost from your balance because the computer cannot define the number. That's how the round off error works. Of course, computers do not round off numbers, they truncate them. Since it cannot save this number, it just ignores it. It just takes the numbers that it has or that it can store. The rest of them, we call them, they are truncated or they are chopped. Means they are just cut off. It's not rounding off. It's truncating or chopping these values. Now, these limitations then, of course, are represented in the number itself. It's not going to be stored properly. Of course, if it's not stored properly, then you cannot do calculations on them properly because you are going to end up with errors. We also see here that the exponent determines the range limitations. How much you are going to leave for the exponent, that's going to determine your range limitation. So if you have another one here for the exponent, then you could have gone up to 10 power plus 99. So you increase significantly your limit of the range of values that you can define. So the exponent determines the range limitations, whereas the significand or the mantissa plays a minor role in determining the range. That doesn't really have a much of a say in determining the range of the values, because whether you define 9.9 into 10 power 9 or whether you define 9.99 into 10 power 9, it doesn't really much have an impact on the range of values that you can define. Of course, it has a small role that it plays in finding the range, but not the big role which is given by the exponent. However, the significand has a profound effect on specifying the precision. How many digits you allow for the significand, the more precision you can have in your values, because you are going to have more significant figures in the values if you allow more digits for the significance. By default, MATLAB works on the IEEE 64-bit system, and from these 64 bits, one of them is used for the sign, and then we have 52 bits for the mantissa, and then we have the 11 bits for the exponent. So from 64, one goes for the sign, 52 go for the significant, and 11 go for the exponent. Yeah. Where is the? Yeah, this is in the assembly level programming. The computers define them. Therefore, we prefer to use MATLAB, and we don't use other languages. So, for example, let me just complete this, and I'll tell you. Going on to all these technical details, then the largest possible number that MATLAB can store is 1.7997 into 10 power 308. So it's a very big number because you have 108 zeros after the decimal point. So that's a very big number. So hopefully enough for all our calculations. And the smallest possible number which MATLAB can store with full precision is 2.225 into 10 power minus 308. Of course, that's 0.00 with 308 zeros. So of course we can say that it's quite a bit of precision that you have with these values. Now if you work with something other than MATLAB, let's say we have something called Visual Basic for applications, VBA. I have worked with VBA, and VBA, even if you are working with small calculations, like if you make a loop and you keep adding 0.001 and you want to stop at 10, you find that the loop doesn't stop at 10. At the end, you'll find the value of 10.0001. Which is wrong. You cannot end up with this value because you are adding only 0.001. But because the way it is dealing with numbers, it doesn't have this precision like MATLAB. It just loses the number and the values there. So you end up with these problems, which is a very big problem that you end up with if you are working with calculations in VBA. Because of this limitations, you end up with getting wrong answers. But MATLAB has a fair bit of precision there because of all this standard that it is using. The machine epsilon, which means the maximum relative error between a number and MATLAB's representation of that number, is 2 to the power minus 52, which is 2.2204 into 10 to the power minus 6. Of course, that's a maximum relative error that you get between a number and the MATLAB representation of the number. So that's the maximum error that we expect to get between the number and its MATLAB's representation. So we can see that it's very small number, not an error of 0.001%, but 0 followed by 16 decimal places. So quite precise. Therefore, we prefer to use MATLAB for our calculations. Now we said this is why round off error happen because of the way computers represent numbers, and also we said sometimes the way that we are doing the calculations also has an impact on the round off errors. For example, if you have large computations, you are doing calculations and you are doing a loop. As I gave you this example of the Visual Basic, it keeps adding and eventually you end up with a big error. So the error was small, let's say it is very small error, but if you keep making a loop and you keep repeating the calculation, the error might build up and then becomes a significant error. Adding a large number and small number, that I'll go to the next slide and show that. We'll go to smearing. Smearing is when an individual term in the summation is larger than the summation itself. For example, if you have this summation, which is x plus 10 to the power minus 20 minus x, and of course mathematically x and minus x cancels and your answer is minus 20. Now what if x is equal to 1? Now this is the meaning where individual term x is equal to 1, and 1 is much bigger than the final answer that you expect to get, which is 10 to the power minus 20. And what happens that if you define this in MATLAB, you define x as 1, and then you write this command. MATLAB doesn't give you 10 to the power minus 20. It gives you a 0. And now if you are expecting to get 10 to the power minus 20 and MATLAB gives you a 0, then of course your calculations are going to be all wrong that you use from this. Can MATLAB not define 10 to the power minus 20? Of course it can define. It has a limit of up to 10 to the minus 308. So it can define that. It is within the range. But this is the process called smearing, is when individual term in a summation is much larger than the result of the summation, then you end up with this problem, and MATLAB gives you a 0 instead of giving 10 to the power minus 20. Although you have in mind that MATLAB can define this number, so you should be expecting to get 10 to the minus 20, but MATLAB gives you a 0. And of course, if you have more calculations after this, then you are going to end up with errors in those calculations. Simplest thing is that if you were going to divide by this value, dividing by 10 to the power minus 20 is going to be different, and dividing by 0 is straightforward. A division by 0 error, and your calculation just stops there. Adding a large number and a small number. Now, if you add 4,000 with 0.001, then what it does, that it has to bring them both to the same exponent if it wants to add them. So 0.4 into 10 power 4, and this becomes 0.0001. It adds and you get this value. But if you have only 4-digit mantissa, then 1, 2, 3, 4, and the rest of it is chopped. As I told you, it is chopped or truncated. And because of this, the rest of it is lost, and you just end up with 4,000 as if you never added any other value to it. So imagine you had a loop and you add this 1,000 times. It won't add anything. Every time you do it, it just gets rid of this. And you thought, I'll add it 1,000 times. So 1,000 multiplied by 0.001 is 1. So I expect to get 4,001. But you end up getting only 4,000 because all that other was lost and it has never been added to the value. Of course, the book gives you these extreme examples using only a 4-digit word size, although we have seen that MATLAB uses 52 bits for the mantissa, but these are just examples brought to you to understand why we end up with these errors. Subtracting 26.86 from 36.41, of course, you end up with the result of 0.9550 because you are going to end up with 0.0955. You cannot have it like this. You have to have a number there. And once you do that, then it moves everything to the left. It adds 1 0 here. And you find now that you have a extra 0 added to the result, which was not supposed to be.